Okay. Hello, everyone. My name is Lindsay Malchinari, and I lead the academic program for Gurobi optimization. Thanks so much for joining us for today's webinar about the AC optimal power flow problem, where we're going to describe the state of the art in the ACOPF problem in the core technical computation and management of power grids. Please feel free to ask questions during the session using the Q&A feature of Zoom. We're going to try to get through all of the questions as we go through the presentation today. But I did want to note we have two members of our technical team, Yuri and Rodrigo, who are going to be available throughout the webinar to answer questions as they come up. Our speaker is going to spend about 10 minutes at the end of the session answering audience questions as well. Again, we are going to be using the Q&A section of Zoom rather than the chat window. Today's webinar is part of the academic webinar series, which shines the spotlight on the academic community, and we're so lucky to have Professor Daniel Bienstock from Columbia joining us. Dan Bienstock is the Liu Family Professor of Operations Research at Columbia University with a joint appointment in Applied Mathematics and Electrical Engineering. He's also been an Informs Fellow since 2013. Dan's main research concerns high-performance algorithms for large-scale optimization with a special focus on hard problems arising in engineering. A specific area of interest for him concerns operations of power grids. Dan's on sabbatical this year, and we're lucky to have him working with us at Gurobi during the sabbatical. Welcome, Dan, and over to you for the webinar.
Thank you, Lindsay. It's a pleasure to be here. I'd like to thank Gurobi for making this all possible. We have a lot of material to go over. By necessity, the talk cannot be complete. In particular, this being a very rich field, I will not be able to provide complete citations for all prior work. It is impossible. However, we will provide links, and I'll be able to answer questions after and be on the talk. So here's a quick outline. What is electrical power? What is ACOPF? How is it used in practice? I can see that the attendees span a very broad set of people, very broad communities. However, what it should be in common is that we are all interested in optimization. So I will provide some details about how optimization is done in the context of ACOPF. And also throughout, I will give some information about Gurobi's interest in ACOPF and what Gurobi is doing about it. Despite what the last bullet point says, questions are not welcome during the talk, but definitely welcome after. Okay, now, before we get started, here's my philosophy about practical optimization. In this field of operations research, over the past decades, there has been a lot of interest in applications of optimization to topics such as logistics and transportation, supply chain, and so on. Those give rise to very particular types of optimization models. And these problems will definitely remain relevant. If anything, they will grow. They're not going away. However, the future holds more. The future also includes applications to heavy engineering and hard science, more and more of those. And those are very different models. If you're not familiar with applications in those domains, those are very different models, very complex models with a very hard rules that do not bend. They represent physics, high level of modeling detail, very large scale models, lots of details in very complex systems. And the performance requirements are very demanding. You have to get solutions fast, good solutions fast, despite the scale. The question is, are our favorite algorithms up to this task? Can they deliver? Okay. Now, power grids, this being a term that is not necessarily a term that is deployed by power engineers. They might use the term power systems. Well, however we call them, they are changing. Renewables are one of the reasons that power grids are changing, but grids were changing regardless of that for many reasons. So there's more consumption of electricity, for example. A lot of the equipment is old and has to be replaced, and that is expensive, and that is making people take a second look and see where they can get efficiencies from. There's the issue of smart loads. These are, by this we mean consumption of energy that is responding to price signals, following algorithms in an intelligent way. That is also related to so-called demand response. It's similar. And also the idea of local generation. Today, most of the generation of power comes from far away. It's conveyed by the power grid to your home. But we are moving to an environment where people will own generation assets, including in their own homes, and they will be selling power. And how will this impact the grid? These are questions, and the algorithms that are used today to operate the grid. So power grids are changing, and this is spurring a lot of interest in the main optimization task that is used to operate the grid. Here's an outline of how the so-called power grid operates in North America today. There are 3 electrical circuits. Everything is in there, including Canada and parts of Mexico as well. Okay, each of these circuits is separate from each other. They are too big to operate as one unit. They are too diverse and too large. So even though they are 3, each of them is one electrical circuit, they are not operated as such. Instead, they are divided into smaller, let's call them markets. And here's a partial map of some of these markets. Each of these markets is controlled either by a so-called ISO or an RTO. And some care is taken so as to separate each of these markets from its neighbors. They are still one electrical circuit, but this is controlled so that in effect they are operated independently to some extent. Now, within each market, or each ISO or each RTO, and here's the picture. This is the New York ISO. This is the size. The word bus is what people in OR might call node. And they would use the word branch or line to represent an arc. To the right, we have a close-up of the New York area, New York City area. It has 1814 buses. This is a realistic rendering of the real system. Some of the data is not publicly available. Some of the data is publicly available. The total number of generators is over 500, including wind farms and so on. By the standards of power engineering, this is not really a large system. You might see much bigger ones, and we'll see some of them later in the talk. All right, now, there's no way that in 1 hour we can educate everybody on the topic of power engineering. It is impossible. This is a very mature topic. It's a deep engineering topic, over 100 years old. It intersects with physics, and there is a lot of engineering. And so we can cover some of the basics here so that at least some of the language is understood. So the word energy, so we cannot define the word energy. Let's take it as a given. Energy is energy. Now, what is power? Power is energy that is instantaneous. So if you have a generator that is producing energy at any instant of time, it's producing power. If you take the integral of power over time, then you get a total energy production by that generator. But the amount at any given instant may vary. And that is the amount that we use the word power. It's energy per unit time. What is electrical current? Well, this is just a movement, or maybe we should say agitation of electrons that are conveying energy, conveying power. Voltage, what is voltage? Voltage, the classical physical term is that voltage is potential energy, but think of voltage combined with current. Voltage refers to how energized the electrons are. It's think of it as the amount of energy per unit charge. How excited are these electrons? How hot are they? The product of voltage and current is power, has units of power. How about alternating current and alternating voltage and alternating power? So we'll get back to that in a minute. The basic science goes back centuries. We see all of these names that we are familiar with. The picture on the left is Maxwell. Okay, Maxwell codified a lot of the equations that control electricity and magnetism more than 100 years ago. Okay, this is classical physics, which is now superseded by quantum mechanics, and we will not go there. So this is the basic science, and the modern engineering details that are used to operate power grids are no less complex. It's, again, I want to stress to the non-power attendees that this is a very deep topic. It takes a lot of reading to become familiarized and to understand how they think and how they deal with complexity. Okay, now here is a toy image of how power is produced at a traditional generator. You have some energy source, some fuel that is burned. This is your typical thermal power unit. When you burn this energy source, the heat is used to boil water that generates steams. The steam drives this piston, and the piston is used to make this thing called the rotor rotate. We'll see a picture of the rotor. This is a massive electromagnet. It is spinning in the US would be 60 hertz. In Europe and other countries, it might be 50 hertz. However, it's a large number of revolutions per second. As it spins very fast, it's generating a magnetic field that is changing because it's rotating. It is spinning inside this cylinder called the stator. They don't touch at all. Now, the stator is static. It does not move, but it has bundles of conducting wire that are looped inside. As the magnetic field changes, it is inducing current, this being one of Maxwell's laws, that a changing magnetic field induces a current. And it's going to be an AC current. Here we have a picture. This is the current. This is an AC current. It's a sinusoidal function. It is inducing a current at a certain voltage. The voltage is the red curve. It is also a sinusoidal curve. The units are different. So the peak for the red curve is different than the peak for the blue curve. But it's also a sinusoidal curve. People in engineering would refer these as phasors. Okay, and the product of current and voltage is power. And power will also be a periodic curve. And here we have it, okay? But the generator is producing current at a given voltage, AC current at a given voltage, and the product of current and voltage is power. And this is how power is generated in a traditional generator today. Here we have pictures of generators. This here is the rotor, and that is the stator. These are generators that are being assembled, they're being built. Okay, you can see the scale of these things. They are not small. This is the beginning of the rotor. Then there's a bigger part inside. Here we have another picture. They are massive. They are massive. They weigh a lot, and they are rotating very quickly. And they don't touch the stator. Here's the picture of the stator. And the holes are being used to loop the wires, and also for cooling, I believe, the conducting wires, and for cooling. Okay. Now, let's now describe this standard alternating current optimal power flow problem. This is the big optimization problem, first formulated roughly 60 years ago. So we have a power system. Here we have a picture of a power system. This is a generator, and we have the loads. Here's a load. And then in between, we have the network. This is the high voltage wires that you see if you drive down the street or down the road, and you see them above the ground, high up. In between, we have these things called transformers that boost voltage and keep power constant. And here, these transformers lower voltage. So we have a power system like that. And at every node, we have a load, which is a demand. There's a numerical power. Okay. And the objective for this optimization problem is to meet the demands at minimum cost. All the cost is incurred at the generators. This is the cost of generating power. And power flows are going to follow laws of physics. We cannot route power any way we want. The way that it is done will have to follow the laws of physics. So let's take a look at that. Okay. Here we have a picture of a power line or a branch between two buses. For the sake of this talk, let's do it the way that power engineers would do it. This is our representation of voltage. Remember, voltage was a sinusoidal curve. Here we are representing voltage in terms of, well, let's go back. Let's go back. We have an amplitude for each of these curves. We have an amplitude, and notice that the peaks are not happening at the same time. They have different phases. So we have to keep track of the amplitude and the phase angle. And this is what this formula does. This is the phase angle, and this is the magnitude. And J is the square root of -1. And so we are representing voltage as a complex number. That is something that we'll have to leave alone for the time being, because in principle, in terms of the picture that I showed you, we cared about the what would be the real part of this. And so what is the imaginary part? So let's leave that alone for the time being, okay? And so we have a voltage that's represented by this quantity, this complex quantity, including the phase and the magnitude, and another voltage here. Let's define theta km to be the difference of the phases. Then basic physics, we will see the basic physics in a minute, indicates that the power from K to M follows a formula like that, okay? What are these quantities? Let me go back. So what are these quantities? This one, that one, this one, that one. So let's take a second look at this formula. Okay, here we go. Here's again the power line between K and M. This is the power injected at K. SMK will be the power injected to the line at M. There's going to be a matrix that is physical properties of the line itself. It's called the admittance matrix. It's a complex valued 2 by 2 matrix. These are all numbers that come from the data. Think of it for now as related to the resistance of the line and so on, or more properly, the impedance of the line. But this is called the admittance matrix. Then Ohm's law says that the current injected at K into the line follows this formula. Y times Vk times Vm. And furthermore, the power, the complex power injected into the line is the product of the voltage and the current, conjugate. The first time that I saw this formula in a textbook, I kept looking for the footnote. You know, where's the footnote? No, it's not a footnote. It's the complex conjugate. And so here we have the formula again. And if you plug in all the quantities that I have over here in terms of the matrix Y and in terms of the phase angle, you will see that the complex current is exactly given by this complex formula. And the complex current injected here at K into the line, we are injecting, so the complex power injected into the line at K. So you're injecting power at K. Some of it will arrive at M. Now, SMK is the reverse. Now, in general, the SMK is not the negative of SKM. They're different. SMK is also given by the corresponding formula. SMK will be, well, Vm times the Y times Vm times Vk. It's the same type of formula. And if you plug in the values or here, you will see that it's not the negative. So you're injecting power into the line here, you're injecting power into the line there. This is complex power. The real part in principle is what we care about, okay? Some of it that you inject here arrives there, some of it does not. What does not arrive is the loss. The line will lose power. And that's an important consideration. What else do we have? Then we have balance constraints. Okay, here we have a bus K. If you add the power balance, injected into all the lines over here, what is that equal to? Well, this is the net amount injected by K into all these branches. And that is the amount generated in total. This is all the generators. This is the total amount generated at K minus the demand that there might be at K. And so this is the net balance. And so this is like a power balance constraint. And so now we have the basic OPF problem, which says minimize the cost of generation at all the buses, okay? Subject to the physics, this is what I wrote before. Subject to flow balance, this is what I wrote before as well. Each branch has a certain limit on the total power it can carry. And then there are voltage limits and generator output limits. And this is the classical ACOPF problem without any adornments, any other side constraints, as formulated a long time ago. Okay. There's an equivalent formulation as a QC-QP, or quadratically constrained quadratic program, as follows. Let's say that we represent each voltage in Cartesian coordinates and rectangular coordinates, a real and an imaginary component. If you simply plug in this expression in here, you can see that you will get a bilinear expression for power in terms of the E's and the F's. And that gives you an equivalent reformulation of the problem using Cartesian coordinates. And we'll see that again in a little bit. So that's our optimization problem. You can think of these constraints as describing what you can do in terms of the physics. There's a classical paper written by well-known people. Ian Hiskins is a highly respected power engineer, not OR person, not optimizer, but a very smart person, good mathematician, but a power engineer. This is how they represent a 3-node network. And here's a projection of the feasible set of solutions to a subset of the coordinates. In total, the ACOPF problem in the polar coordinates for this network has about 30 variables, 30. So this is a projection to a 3-dimensional subspace. And you can see how complex it is. This is a set of feasible solutions. If you're solving an optimization problem, like the one that I showed you before, you have to pick a point somewhere in here. And I want to stress how important it is, this being a paper written almost 20 years ago, how important it is that the constraints given by the physics have to be satisfied. You know, they stress that a lot in this language that they wrote. Okay, here we have again the ACOPF problem. There's a common simplification where we assume that the voltages have unit power. The power engineers have a very clever scaling system. So you scale all physical quantities so that they all have reasonable values. As we know from other optimization problems, scaling is very important. Scaling in linear programming is very important. LP solvers deploy automatic scaling strategies. With non-linear problems, it's a whole other story altogether. It's very difficult to come up with reasonable scaling setups. The power engineers have developed one over many years so that when you're solving a problem, the quantities that you're given are already scaled. In particular, the voltages are all roughly about 1.0. And this so-called DC approximation, they're said to be exactly equal to 1. What else? The other assumption in this simplification is that the phase angle differences across a line, like what I had over here, across a line KM, the phase angle difference is small. That being a good engineering practice. You want them to be small. Okay, so we assume that it's small enough so that the cosine is effectively equal to 1 and the sine is equal to the difference. And you ignore the so-called reactive power, which is the complex component of power. I'll be happy to take up questions later on as to why do we have a real part in an imaginary part. Cannot do it now. And so you take this equation and you simplify it as per these assumptions, okay, ignoring the reactive power, voltage is equal to 1, cosine and sine being as I said. And now you have an optimization problem that looks like this, okay? Y is one of the entries of that big Y matrix. This is the so-called DC approximation or linear approximation to the optimal power flow problem. It's an LP. This LP gets solved very quickly, even in very large scale cases, very quickly. The solvers do a good job. Okay. A variant of this LP is the so-called unit commitment problem. Here given in a single time period version. You have a binary variable for every generator. The binary variable says, I turn it on or I don't turn it on. If you turn it on, then the generator has a range of power outputs that are available, and you pay a fixed cost. Other than that, it's the same ACOPF problem that I had before. There's a multi-period version of this model, which is more meaningful, where you have ramping constraints, meaning if a generator is off and you turn it on, then the range of power outputs that is available to that generator changes as a function of time. And other side constraints regarding turning generators on and off. So this is the unit commitment problem. This is a very important problem. Run every day. Let's call this bedrock operation. Once a day, you run the so-called day-ahead markets. This is an optimization problem that plans hourly operations for the next day on an hourly basis using demand estimates. The generator owners submit bids for how much they want to charge for making their generator available. The optimization problem, the multi-time period version of this, selects which generators are operated when. And in the parlance of the industry, which generators are clearing the market. Once the MIP is solved, and this is given 3 or 4 hours, then the binary variables are fixed. The problem is solved again now as an LP with the binary variables fixed. And the dual variables for these constraints are used as prices, the price of energy at bus K. In the multi-time period version, the price of energy at bus K as a function of time. And this is used to operate the markets. Different countries have different versions of the ideas that I just described. As the day moves forward, the demand estimates are becoming corrected, they're becoming firmer. The optimization problem effectively is rerun. When you get to about within 5 minutes, the pure LP version, this is run again, now using the latest estimates for demands, and the dual variables for that are used as actual prices that everybody either pays or gets paid for, okay? There's a long-term planning version run once every few months where you have very broad estimates for demand moving forward, and the generators who want to participate in the day-ahead markets have to participate in this long-term planning model. They have to effectively submit bids, and a MIP, like what I described before, is solved again using very broad estimates. This is just so people get committed. Generators are committed to being in the day-ahead markets. Notice these are all the linear models. The AC model is only used today for studies, offline studies, or in the course of the day to make sure that this linear approximation is safe enough in terms of the physics. Moving forward, however, the AC models are going to be run more and more frequently. Effectively, the goal is to get rid of the linear version. The reason being that, as I mentioned before, the grids are changing. They are getting closer to risk. There's more uncertainty involved. And so the need for accuracy in the modeling is more pressing. Okay, now, how do we solve? Now we're moving into the interesting part of the talk. How do we solve ACOPF? If you come from the optimization world, the linear MIP world, you would say, well, I want to solve this MIP. In the AC world, it's more nuanced than that. The question is, do you want to get a good solution without knowing how good it is? Do you want to prove a lower bound? And they are really very different questions. And now, how about extensions of this ACOPF problem to mixed integer variance? What do you do then? The issue there being, well, when do you know that a solution is actually good? It's a little more complicated than when you don't have the mixed integer setup. Okay. Let's begin with the fun part, good solutions. There's only one method that today you can deploy, which is the interior point methods. If you're interested in ACOPF, you have to have one of these. There is no alternative, none, zero. What do you have? Well, there's nitro and IP-opt, very good, both very, very, very good, very capable. However, I want to point out that even very simple implementations of log barrier methods for ACOPF do quite well, okay? And nothing comes even close. The theory, I should say, the theories behind nitro and IP-opt are very nice, very elegant. If you're not familiar with that theory, I encourage you to look at the papers. There are many papers. What does the theory do? Well, it only goes so far. ACOPF is non-convex optimization, NP-hard, whatever you want to call it. The theory only guarantees convergence to a critical point for the barrier function. These are barrier methods, and that's it. That's it. That's all that the theory guarantees. Cannot guarantee anymore. However, on standard ACOPF, really excellent solutions are computed even on the largest cases, and I'll show you some of that, okay? There are limitations to the statement I have made. These excellent solvers, nitro and IP-opt, they do run out of steam on the biggest cases on multi-time period models. They do not deliver. It's just too big. The QC-QP formulation is weak compared to the polar formulation. This is an empirical observation. So this formulation with sines and cosines and all that, well, that's the one to go with. Not the QC-QP formulation that looks familiar, perhaps. An issue is that with these interior point methods, you cannot expect the same kind of tolerances. You get some infeasibilities. You don't get exact solutions. It's even questionable from a fundamental standpoint. What is an exact solution? The quantities are going to be, if you play around with a toy small problem and you analytically solve it, you get irrational quantities. This is new. You don't get this in the LP case. There's a whole range of pathological behaviors that in principle are possible. And we are punting on those. We are ignoring those. Okay. Here are some sample runtimes. These are publicly available synthetic systems. The bigger ones are very realistic. The numbers, you can see that the names have a number. The number refers to the number of buses. This is a nice practice that the power engineers have adopted. They tell you in the name of the case, they tell you how big it is. This one is pretty massive. Now here I have the solver that I'm calling MIPS. This is a publicly available solver. It is what I casually referred to before as just a casual implementation of the log barrier method. And notice that it actually gets a solution very quickly. Even this one, this is in seconds, okay? Now, when you cross this kind of threshold, the problems there are several in between. The problems become harder, okay? I can only run nitro and IP-opt. They run for roughly the same amount of time on a normal computer on this example. This is a big one. Now, of course, the question is how good are these solutions? Okay, so we are right back at the critical issue that I cited before. How do you know if these are any good? Because the solver doesn't tell you. You run IP-opt and nitro, it gives you the solution. You plug it in, you verify that it satisfies the inequalities up to a certain tolerance, you get the objective value, and that's all you get. No guarantees of anything. Pretty fast though, but no guarantees of anything. So what are the convex relaxations for ACOPF? Now there's a reason that I'm interested in this from a research perspective. From a research perspective, I would like to have an alternative to nitro and IP-opt. I would like to have a different technology that is closer to something that comes from a relaxation. Ideally, something that you can prove something about, that if you run it long enough, it could be a long time, but if you run it long enough, you will get something that is guaranteed. Nitro and IPOP eventually do not scale to the largest examples, largest multi-period examples that we want to solve. They are excellent, but they don't get there. I would like to have an alternative. And so this is why I'm interested in this. And so I'm interested in relaxations so that I can go from a relaxation to a solution method. Okay, now I should mention that Gurobi today does not have a log area solver that can be deployed to an arbitrary nonlinear, non-convex problem, something with sines and cosines. Gurobi is very interested in developing something like this. I would say that they're working on it. Nitro and IPOP represent a massive amount of work spanning many years, and they're very mature systems. Gurobi is not there yet, but they're interested in it. I would say Gurobi is also interested in having a solution method that is based on a relaxation. Gurobi today ships with a QCQP solver. I'll describe the basic fundamental methodology that is involved in such a solver. Gurobi, in principle, also will compute solutions. There's an NLP heuristic in Gurobi. If you have Gurobi 10, and even before 10, you have that heuristic. We'll discuss that in a bit. Okay, so let's go back to the QCQP formulation. So this is how we were doing it. We take the basic physics, which is this. We take the rectangular representation of voltages. And if we plug them in here and there, we'll get the correct expression for power, which is going to be bilinear because we have products. In fact, we have these expressions. The real part of power is given by this nice formula, and the complex part of power is given by that formula. And the B's and the G's are numbers in the Y matrix. So this is data, okay? This is all data. The bold quantities are the variables that we have, and you can see these are bilinear. Nasty, right? It's bilinear. Well, what can you do? We start from this. So you're not going to get something that is trivial. Okay. So what do we do about solving an optimization problem with real variables, but with bilinear expressions? The workhorse is the so-called McCormick relaxation or reformulation. This is well known. If you have a bilinear expression and you want to linearize it approximately, where the variables x and y are in ranges, the convex hull of the numbers w subject to x and y given by these ranges is given by 4 linear expressions. And so if you have an optimization problem with bilinear expressions like that one, you introduce a new variable. In this case, we're calling it w. And then you add these inequalities, and now you have a relaxation. Of course, it's not exact, but it's linear. This is a very pretty picture that I got from Wikipedia. I have no idea, I should say, what the picture represents. It's probably wrong, but it's pretty. Now, this works well with so-called spatial branching. Spatial branching is like branch and bound, except there'll be a branching on continuous variables. So if we have solved a relaxation, let's say like one where we have done all of this for every bilinear expression, we pick one of the variables x, and now we split it. We split the bound, this range between xl and xu using some intermediate value. And we branch. On one side, we are on one side of the new range, and on the other side of the branch, we are on the other side. And when we branch, we tighten up the McCormick's because the lower bounds and the upper bounds on x will change, will be different depending on which branch you're on. And now you have in each side of the branch, you have a tighter representation that you had before. So that is spatial branching. And this is McCormick. And combining the two, you have a valid algorithm. If you fathom a node because of infeasibility, well, it's gone. If at some point you solve a node, you solve a relaxation, and you check that W is given by X times Y, actually given by X times Y, is very, very close to the estimate for the W that you're getting from the relaxation. And this being true for every bilinear expression, then you can say, well, my approximation is good enough and I can fathom the node. I have found a new incumbent solution subject to tolerances and such. What else? There are cuts that one can add. There are the whole families of cuts that one can add, okay? How well does it work on ACOPF? So if we do this for the power expression, how well does it work? So this is Gurobi. This is the Gurobi QCQP solver that does spatial branching with McCormick and with cuts. And the answer is it does not do well at all. Okay, this is the case 9. This is a 9-node network, a 9-bus network. The interior point method, this is the value that it computed. We can see how long it takes for all of these cases to get anywhere near the actual value, which a posteriori turns out to be optimal or near optimal. Okay, so the interior point method really is solving within tolerance, solving all of these cases. Spatial branch and bound on ACOPF does very poorly. Okay, notice in this case there were some numerical issues. You know, the lower bound proved is bigger than the upper bound. But okay, why so bad? And how about upper bounds? Because the upper bound that we have is that computed by the interior point method. In other words, the QCQP solver is not finding the upper bound. So what can we do about that? That looks pretty hopeless, I should say. Okay, now, here's a critical observation. We would like to tighten up this QCQP formulation. And so here's, again, this so-called active power representation in the polar form. So let's introduce some auxiliary variables. You know, this variable is meant to represent that. That variable is meant to represent that expression, what we see here. And that one is meant to represent that expression. If we sum the square of this plus the square of that, namely this and that, you exactly get that this is equal to the product of these two variables, the variable that represents that and the variable that represents that. That's because sine square plus cosine square is equal to 1. We can relax that into a rotated cone inequality. This was discovered by this gentleman named Jabber. These new variables, C and S, can be related to the rectangular coordinate formulation. This is the C variable and that is the S variable. And so we can add this inequality. Okay, this is an observation that is non-trivial. It's a non-linear observation, does not follow directly from the linearization. If I just wrote this, I could obtain that. You can check that this is true in terms of these bilinear expressions, but the solver is not going to do that. The solvers are not going to take linear combinations of squares of expressions. Okay, but you can add this baby. Now here is the QCQP formulation, the bilinear formulation for ACOPF. Here are the non-convexities. And here is the alternate representation, relaxation, using this Jabber inequality. Notice that at this point, this is very distant from the original problem. There are no voltage coordinate variables. They're all gone, but it's a relaxation. We want to prove good lower bounds. This is a relaxation. How well does it do? And the answer is it does quite well, okay? This is now, remember how poor this was without the convex, the second order, this rotated cone inequality. It gets very close now to the true optimum, very close, okay? Even for this case, it's about 2% away. The run times are, they're creeping up. For larger examples, well, nobody converges. Nobody can solve the second order cone program. Gurobi does not converge. MOSEC does not converge. A range of other solvers fail to converge. The second order cone problems are becoming difficult. Okay. Now here's a trick that one can play, right? Let's go back to the original QCQPs. We can see that the root relaxation was very weak without the Jabber inequality. It was really very, very weak. It's a lost game. So we could add the Jabber inequality to the QCQP, and run that. Then we will have a problem where the value of the root relaxation should be tight. After all, it says that it should be tight. So what happens if we do it for this one? Oh, wait a minute. The value of the root relaxation is very weak. Why is it very weak? And it takes a long time. Why does it take a long time? Well, it takes a long time. Well, let's put that aside for the time being. Why is it weak? It shouldn't be. It should be at least that much. The issue now being that when you run spatial branch and bound, you anticipate that you will have to enumerate a lot of nodes. You want those node solve times to be very brief, to be very fast. Second order cone programs, big ones, are not easy to solve. So Gurobi and other solvers, very wisely, they will use an outer approximation of the rotated cone inequalities to some tolerance, so that they are actually running an LP and adding cuts on the fly to better approximate these rotated cone inequalities. But in doing so, the quality of the rotated cone approximation deteriorates very rapidly, very rapidly. And so you get the worst of both worlds. You get an LP now, you get a big LP because you're approximating these rotated cone inequalities, each of them with quite a few linear inequalities. So you have a big LP. The big LP is still weak, and it's also expensive. So this is not working too well. Okay. Now, what can we do about this? So the problem is, in theory, adding this inequality tightens up the formulation a lot. We see that happening. But we don't like the fact that it's a rotated cone inequality. By doing that, we're making the relaxations hard to solve. We would like to have a linear inequality. Now you might say, how about that? How about that? That is also, this is a convex quadratic inequality. Well, this is not a problem because in a realistic power grid, in a realistic system, these inequalities usually will be quite slack. We can almost pretend that they're not there. Okay. On a realistic system, most lines are not congested. Maybe a handful of lines, like 3 or 4 out of several thousand, 5 out of several thousand may be congested, but the vast majority of these inequalities will not be tight. But these will be tight. That's a question. Why do they need to be tight? These all will be tight. And they make the rotated cone problem hard to solve. So we would like to do something about this. So what can we do? Okay, now here's an observation. Here's an observation. I wrote a paper with my former student Gonzalo in 2014. This observation has also been made by other people since, which is, and it follows from the physics, which is that if you take this expression and you add it, you obtain something that in the physical sense is the power lost in the line, which is always going to be a non-negative inequality. And now what we're going to do is we're going to let go of the complicating rotated cone inequality and use the linear, this inequality. And so now we have this, which is for all practical purposes an LP. Of course, the objective is convex quadratic. Let's put that, let's ignore that for the time being, okay? But this is now a great simplification of what we had before, which was that, okay? So what happens if we do that? So now we can see the following. So in dark color, I have the LP value. In light blue, I have the rotated cone, the second order cone program, and the same with the runtime. So you can see the runtimes are a lot smaller for the LP, and they get smaller and smaller. However, for the bigger examples, the rotated cone program cannot even converge. This is what I forecast before. This is Gurobi and Mosaic and other solvers. Potentially, if whoever wrote the second order cone solver for Gurobi is given this case, they'll be able to do something so that they can solve. I mean, out of the box. And the same with Mosaic and all the others. But out of the box, they cannot solve it. And that is how long it takes you for the solver to tell you that it couldn't solve it. But the LP still, at this point, this being this really huge one, it's about 10%, a little more, a little less away from the optimum, but still, it's within practicable runtime. Okay, and now why does this all happen? Why is it that this rotated cone inequality improved the tightness so much? If you write the power flow equations and you add them up, you get that this quantity that I call the loss is always equal to some positive amount times this expression in terms of these new lifted variables. Now, in terms of writing this inequality, that inequality mathematically implies that this is always non-negative. This is an outer approximation to this conic set. If you tell me this is valid, then that is valid. Well, if that is non-negative, that means that the loss is non-negative. So writing the Jabber inequality implies that the loss is non-negative. And that's something that was not known. Moreover, writing this fact over here implies that if you take a solution to this problem, you can decompose the P's into flow paths from generators to loads, thereby accounting for all of the load and all of the losses as well. If we didn't have this expression, if we had a negative amount, then effectively what that means is that this line Km is made as a free source of energy. The negative, if you have a negative loss, the negative of the loss is effectively a free generator with cost 0, thereby giving you a poorer bound. And this is why all of this works. All right, now there are other convex relaxations. I don't have time to talk about this. Moving forward, this nonlinear formulation will become much more widely used together with binary variables for so-called topology optimization, turning branches on and off. Configurable components, by this what I mean is that this Y matrix that I described before, which are physical attributes of each branch, well, these are controllable. You can use integer variables to decide what the values should be through very complicated formulas. That can also be optimized over. There's an ongoing grid optimization competition or competitions in which I have participated, I'm participating, that have such features. Large-scale problems, multi-time period, many complicating features, and also models of markets. Quite interesting, very challenging. No time to talk about it now. What I would like to do now is that I would like to show you a little bit about things that Gurobi is making available moving forward and very soon. So let me show you something. Just give me 1 second, and here we are. So Gurobi is going to make a module publicly available called Optimods. This is going to happen very soon. What Optimods does is that it tackles a number of optimization problems from the ground up, giving you some data and also giving you code, showing you how to do things using Gurobi done the right way, Python code. Among those, there's an optimal power flow module that is about 90% ready or 95% ready. It gives you, so this is this web page that will be available to you. First of all, there are citations. These are all pretty good citations. I took the liberty of including my own monograph on that. But these are all very good textbook. This is a very good, very thorough survey on convex relaxations for ACOPF. Very nice. The basics of power is being explained here. You saw this in the slide. There's a tab for ACOPF, including the various optimization problems and the relaxation, the QCQP. There's another tab for DCOPF, this being the linearized version, and the optimization problem, what I described. This is the topology optimization, where you have a binary variable that tells you whether a line is operating or not. Okay, so we have that all there. Now, in addition, there is code, okay, that will be made available with the Optimods. Let me go back a little bit. Power flow. Okay, here we go. And it's this Python code. There are examples here. I would like to run some of this code. And I think we have time. We have about 4 minutes left, but it's Python code. And there are calls like that call and other calls that I'll show you in a minute that show you how to use Gurobi properly to tackle these problems. Let me go back. Let's see if this is a good one here. Yep. I'm going to run an example here. This is a MIP. This is an example of this problem. This is the DCOPF problem, linear, with a binary variable for every line. So you're trying to minimize the cost of generation, but you're allowed to turn lines off. Believe it or not, because this is a non-convex problem. I mean that once you allow lines to be turned off, you may save a little bit. Okay, and that's the problem. So let me run this. I'm going to run it in two different ways. So here we have Gurobi running. It read this case, and now it rendered an image. Let me bring the image over. Here we go. This is New York State without the map. Gurobi is still running. It's solving a MIP. You can see it got a pretty good solution already. This is the first solution it got. And as it finds incumbents, it renders the solution using graphics. And what we see over here is just information about the different buses. You can zoom in on something. Oh, okay, now here's the next incumbent and here's the next incumbent. And what is being shown in red is lines being turned off. And now at this point, it's nearly done. Now, when you look at this, you see, oh, what are these? These lines seem to go all to the outside. And the answer is yes, they're going to different markets. When you see this solution, you would say, well, I don't like this solution. You know, I don't want to be turning off all these lines to go to other markets. I want to keep many more of them operating, you know, just in case I need to import power or something like that. So you can simply add a constraint. You know, when you see the picture, you can add a constraint saying, well, of these lines, you know, turn off at most 5 of them or something. Here is turning off 47. Okay. The other thing to notice is the objective value is already, it's pretty much the same. It is the same to multiple digits. This is an observation that has been made by the industry that this topology optimization problem is one where you don't want to turn off many lines. Not turning anything off is usually near optimal within a few percent. And in this case, it really is almost completely optimal. Okay. Let me see if I can run one of the Optimods modules. Okay, let me go back over here. No, wrong one. Okay, here we go. Okay. Let me cut that. Let's see if I can add some code. I would like to run some code from the Optimods. Okay. All right. And here we go. Let me make sure that I'm in the right folder. One more. And let's run Python. Okay, I'm running Python. Let me just copy these calls over here. It's just Python. It's harmless. That worked. I'm going to run this small case. And here I'm choosing to provide a full path to the case. File is just the name of a file. Now I'm going to use a call to read the data. This is code that we provide. Okay, the data has been read. Let's solve it. And here I'm going to solve the DCOPF problem without branch switching. Okay, it solved it. Let's solve it now with branch switching. So with this is the mixed integer program that allows you to turn lines off. And it did not turn anything off, trust me on that. Let's solve the ACOPF problem. This is the QCQP. Okay, it solved it. This being a small one, the Gurobi QCQP code in this case works. Notice the initial relaxation is terrible, as we noticed before. It's improved pretty quickly. Then it finds a solution that's the optimal solution. Okay, it tells you how many cuts it used of what type. This is positive semi-definite cut. And it's really all done at the root, as you can see over here. And now you can ask for data. You know, you can say, okay, what is the solution? Here we go. Let me copy that guy. So for bus number 5, What is it? What is it? What is the solution? So it's going to tell you that. So it tells you this is the voltage and this is the angle at that bus in the optimal solution. And you can query branches and generators and so on and so forth. So that is Optimods today. We are adding much more. And moving forward, the other thing that we are really working on is on a solver for ACOPF, a solver from the perspective of getting good solutions, not proving lower bounds. We already know how to prove good lower bounds with an LP, that are run very fast, even for the biggest cases. But we would like to get good solutions. So there's going to be a nonlinear solver, and we're also working on an LP-based solver, again, from the solver from the perspective of computing good solutions quickly. And with that, I would like to finish my talk. Thank you very much.
Thank you so much, Dan. It was a great webinar. We have so much excitement coming in for the Optimods. I did hear we are going to be releasing it. It's scheduled to release the end of May, although that date is a bit flexible right now. So stay tuned to everyone, and we will be communicating about it when it's ready and shareable. So we are at the top of the hour right now. Dan, do you have a couple of minutes to stay for questions? We've had a lot come in that are already answered, but we do have a few more that are coming in through Q&A.
Okay.
Okay, beautiful. So I will hand things over to my colleague Rodrigo to take just 2 or 3 questions given time and try to end in the next 5 minutes or so for attendees. If you can't stay for the Q&A, we certainly understand. And thank you again. Please be sure to take the survey to follow. It helps us bring you more content like this. So thank you.
Yeah, great. Thank you all for attending, and thanks, Dan, for a great presentation. We have a question here. Power system studies consider multiple time steps and time coupling integer decision variables are suitable to vendors decomposition by dividing the integer variables and the master and operation problems. Are there any efforts to use vendors in this approach discussed today?
So, okay, there are actually 2 separate questions in there. So this is a multi-time period mixed integer problem with linear constraints. This is solved routinely every day. Gurobi is used by all the ISOs. It runs well. It runs within the allowed time. And it's just a standard Gurobi running there. Now, that is a linear model. For the nonlinear problem, well, that's a different ballgame altogether. I mean, for the nonlinear problem, you know, even without the binary variables, we already have a heap of trouble there, okay? It's possible that something like benders will work, but then again, you know, benders, you can think of benders as an example of a cutting plane algorithm or delayed constraint generation. To some extent, many of us are doing that already today. So that is the state, you know, the linear case is handled quite well by Gurobi. All the ISOs are using it now, and they've saved a lot of money by doing it, as compared to what they did before, which was to use some form of Lagrangian relaxation. The nonlinear model, well, that is a whole other story altogether.
Thank you. Another question is, can you talk about the role of uncertainty here?
Yes, that is very important, okay? That is very important already for the linear case. That is something that we are working on. I'm working on this. The issue here being that you run these day-ahead markets that they have a lot of meaning because people are enter into commitments. The generators are entering into commitments. The utilities that are representing customers are entering as customers themselves, and they're agreeing on prices for energy delivery. These are based on estimates for what the load will be, what the conditions will be a day hence. And then there could be a disparity between those prices and then what happens in the actual real time when the actual demands are accurately known at that point, within 5 minutes, let's say. And there are other uncertainties like wind and solar. And then there can be a disparity between the prices computed in the day-ahead markets and the prices computed in the real-time markets. If a utility is representing a load, a city, let's say, and they have more load, than anticipated, then the extra load will have to be paid for at the real-time prices, which could be substantially higher, and the customers eventually are paying for this. And so this is a topic of a lot of interest now, research interest. How do you modify the markets really so as to make them more risk resistant, more risk aware, and so that the actual financials are better handled, as well as physical risk. If there's a big disparity between the real-time conditions and the estimated conditions that they ahead, the grid may be unable to deliver power. This has not been an issue until now. Now it's becoming more of a concern that the grid may be unable to deliver power the way that things are run now. And so this definitely has to be handled appropriately. It's a subject for research. It's not something that the engineers can roll out today.
Thank you. I think we have time for one last question, and this is related. Do you have any experience or can you comment on how the ACOPF relates to the topology optimization based on the size of the problem?
Yeah, so one empirical observation that has been made in the literature is that in terms of topology optimization, that you have to turn only a few lines off to get the vast majority of the benefit. This observation needs to be further evaluated with wider studies, that are open to everybody to actually see that this is really the case. I think it is the case a good part of the time, but it needs to be, really studied. It's not enough for somebody to get up at some conference and say, oh yeah, it is. We'd like to see the data sets and the runs and verify that this is the case. I think it is the case a good part of the time. It may not always be the case, but the studies have to be done carefully, again, in the context of the previous questions in terms of uncertainty, and in terms of extreme conditions and such. So actually, again, this is a subject for research. So we need accuracy in the solvers and so on and so forth. And this is a technical challenge.
Thank you so much. Thank you all for attending. That is where we are going to end the session today. Apologies if we didn't get to your question. We hope to see you at the next academic webinar, and round of applause for Dan once more. Thank you so much.